All right, welcome to today's Explainer. We are diving straight into what I can only describe as a monumental shift in global automotive strategy. These insights are coming directly from the top engineering minds at the 2026 Vienna International Motor Symposium. Now, if you've been following the auto industry, you know we've been living through this period of just intensely rapid transformation. But here's the thing, the consensus among global leadership has just pivoted sharply. We're actually looking at a fundamental re-architecting of how the world is going to drive over the next decade.
So, let's kick things off by politely shattering a pretty massive mainstream assumption. We have to ask, is the era of EV-only mobility already over? The idea of technological certainty, that belief that a 100% battery electric future is just this guaranteed binary bet, well, that's officially ended. Automotive leaders have realized that putting literally all their engineering chips on a single technological pathway is simply way too risky in today's highly volatile global climate. And this marks a massive paradigm shift for the industry. We are moving away from those risky, single-path binary bets and towards a strategy of genuine systemic resilience. Why? Because we're facing undeniable physical constraints, supply chain bottlenecks, and some severe geopolitical fragmentation. To survive all this, the industry is pivoting toward a strategic, multipolar approach that's actually designed to withstand sudden global shocks. Think of it like building a super robust suspension system for the entire automotive industry, one that's ready to absorb the massive bumps of an unpredictable future.
To make sense of this, we're going to break this 2026 strategy down into 4 interlocking pillars. First, technology neutrality. Second, building a resilient portfolio. Third, the modular architecture mindset. And finally, Sino-European integration.
Okay, starting right off with pillar number 1, technology neutrality as an absolute imperative. Right off the bat, we have to acknowledge the severe roadblocks of an EV-only reality. Global grid capacity constraints are a massive hurdle. Trying to upgrade infrastructure for non-urban charging corridors is literally like trying to push a river through a garden hose. Then you've got high vulnerabilities to rare earth mineral embargoes, which is a huge supply chain risk. If just one country turns off the tap on critical minerals, a singular EV strategy completely grinds to a halt. And finally, the heavy-duty commercial sector, they simply cannot compromise on payload just to haul around massive heavy battery packs. The physics frankly just don't add up for every single use case.
Because of those limits, we're being forced into a major transition. We're moving away from these narrow tailpipe mandates and shifting toward a well-to-wheel life cycle assessment. If we want true climate neutrality, we have to look at the entire carbon footprint. That means everything from energy extraction at the power plant all the way to the vehicle's end of life. And achieving this requires a parallel embrace of e-fuels, hydrogen internal combustion engines, and advanced hybrids right alongside battery electrics. We have to make absolutely sure we aren't just moving carbon emissions from the highway over to the smokestack.
That brings us right into our second pillar, building a resilient portfolio. So to hedge against those geopolitical and infrastructural risks we just talked about, the industry is building highly resilient technology portfolios. They are actively, in parallel, developing ultra-high-efficiency internal combustion and hybrid engines alongside advanced battery electrics and zero-carbon molecules like hydrogen. It's really about having the right tool for the right job. You wouldn't use a sledgehammer to drive a thumbtack, right? Just like you wouldn't use a heavy battery pack for a cross-continental freight truck when a hydrogen powertrain can do it way more efficiently. Whether it's an urban zero-emission flagship car or heavy-duty workhorse, diversification is absolutely the key to survival.
Now, a crucial takeaway here is that internal combustion is not dead. Actually, far from it. Engineers are targeting absolutely unprecedented efficiencies. The main battleground right now is breaking through the 48% brake thermal efficiency ceiling for dedicated hybrid engines and range extenders. Basically, they're squeezing every possible drop of useful mechanical work out of the fuel to maximize that efficiency. By doing this, they're taking the traditional engine and turning it into an ultra-clean, highly optimized power generator for advanced hybrid systems.
But achieving that macro-level resilience, that requires some mind-bending micro-engineering. We are talking about e-axles spinning at an incredible 35,000 RPM. That speed actually slashes the reliance on rare earth materials by 30% simply because it allows you to use much smaller motors. We're also seeing third-generation silicon carbide MOSFETs. You can think of these as ultra-efficient electronic switches that manage power flow inside the vehicle, and they're cutting energy switching losses by 20%. Engineers are literally pushing the extreme boundaries of thermodynamics, electromagnetism, and materials science just to make these multi-powertrain systems viable.
Moving on to pillar number 3, the highly modular architecture mindset.
This brings up a very practical question. How on earth can global OEMs afford to develop all of these completely different powertrains simultaneously? Well, the answer is aggressive, extreme modularity. It's essentially creating a Swiss Army knife of mobility. Let's look at the Traton model, for example. It uses universal thermal interfaces and strictly standardized hardpoints. This literally allows manufacturers to plug and play battery electric, internal combustion, and hydrogen modules onto one unified commercial chassis. They can dynamically switch up their production lines to hedge against sudden supply chain shocks or changes in consumer demand without having to completely redesign the vehicle from scratch. It's brilliant.
But here's the catch. Hardware modularity will absolutely bankrupt a company without software decoupling. And that leads us to the concept of the abstraction stack. See, you can't write custom software for every single physical hardware variation across all your internal combustion, hybrid, and electric models. It's too expensive. You have to decouple the physical machine from the digital logic. The way they do this is through a really clever three-layer approach. Step 1 is your commoditized hardware, just the basic sensors and actuators. Step 2 is where the magic happens, the middleware and the European HAL4STV initiative. That stands for Hardware Abstraction Layer for Software-Defined Vehicles. Think of it as a universal translator. By adopting this layer, engineers can isolate all that hardware variance. Then, step 3 is the software-defined applications, like your AI and smart cockpits. Thanks to that middle translator layer, developers can write complex software just once and run it seamlessly across totally diverse drivetrains. This completely prevents vendor lock-in and saves billions in development costs. Finally, let's head into our fourth pillar, Sino-European integration. When you zoom out to a global scale, you see a deep engineering divergence between two of the major players. On one side, we have China's Roadmap 3.0, which is highly focused on expansive scale. They're integrating battery electrics with advanced hybrids, like REVs, range-extended electric vehicles, and relying heavily on V2X, which is vehicle-to-everything infrastructure connectivity. On the flip side, you have the EU's 2025 Automotive package. They prioritize strict zero-tailpipe emissions, single-vehicle intelligence bounded by super-rigorous GDPR privacy rules, and deeply audited lifecycle carbon footprint thresholds.
So what we're looking at is the ultimate geopolitical collision. China is pushing an all-ecosystem expansion, leveraging their massive domestic scale and rapid software iteration to push outward. Up against that is the EU's defensive fortress, which is constructed from rigorous digital product passports, strict supply chain transparency mandates, and environmental compliance laws that essentially serve as incredibly strict market entry barriers.
Yet, despite these massive defensive walls, the reality of global integration demands a totally new operational playbook: co-opetition. Global Tier 1 suppliers and OEMs really have no choice here. They have to interlock Europe's verifiable data compliance, deep R&D, and mechanical precision with China's agile software loops, extreme cost-down engineering, and unmatched manufacturing scale. Neither side can completely dominate the future of mobility in total isolation. They literally have to work together to make this multipolar strategy viable for anyone. Bringing this all together, the overarching verdict from the global engineering consultants at the symposium is incredibly clear. Stop single-path betting. We must architect platforms for 10 to 15 years of multi-powertrain coexistence. This energy transition? It is not a binary switch. It is a prolonged, hybrid operational reality that absolutely requires what they call a culture of humility. It's a fundamental acknowledgement that this transition is complex, it's going to be long, and it will be highly regionalized. So, as the global automotive industry races to execute this incredibly complex digital physical resilience strategy, I'm going to leave you to ponder one vital question. Will your engineering architecture, or the architecture of the companies you're investing in, survive the next decade of multipolar mobility? Thank you so much for joining me for today's explainer. I really hope this gave you a structured, clear understanding of the fascinating road ahead. Have electric vehicles finally hit a physical wall? I mean, really think about it. For the last decade, we've kind of been living in this era of single variable optimization, tweaking a chemistry here, maybe making a motor slightly bigger there. But the hard truth from the engineering world is that this piecemeal approach has pretty much reached its absolute physical limits. To unlock that next massive leap in range, cost, and safety, the entire industry is being forced to execute a massive structural pivot. Welcome to this explainer. Today, we're going to do a top-down strategic deconstruction of next-generation energy storage. Everything we're diving into today is synthesized straight from the groundbreaking data presented at the 47th International Vienna Motor Symposium.
Think of this as the definitive roadmap for the year 2026, and trust me, it completely rewrites the rules of powertrain engineering. The 2026 paradigm isn't about isolated tweaks anymore. It's absolutely crucial to understand that it demands a tightly coupled, system-level approach across every single domain. It's like a giant puzzle. We're talking about the complete integration of manufacturing processes, the internal chemistry of the cell itself, and how that cell physically communicates with the global power grid. You literally can't change one piece without completely re-architecting the whole shebang.
So, to make sense of this massive shift, we're going to follow three foundational pillars. Number 1, the manufacturing and process revolution. Number 2, chemistry and packaging breakthroughs. And finally, energy integration and topology.
Let's jump right into Pillar 1, the manufacturing and process revolution, and see how the industry is completely rethinking the physical building blocks of batteries to hit massive global scale.
Traditionally, battery formats have been a bit of a logistical chaos. You've got different sizes for lithium iron phosphate, different dimensions for sodium ion, different shapes for solid state. But now we're looking at the unified cell strategy, which is really being spearheaded by Volkswagen's PowerCo. By standardizing the physical dimensions of the outer casing, automakers finally regain control over vehicle packaging while remaining totally agnostic to whatever chemical evolution is happening hidden inside that box. Now, why does this matter to us, the consumers? Well, because this single standardized format covers 80% of a manufacturer's vehicle architectures. It unlocks totally unprecedented economies of scale. It anchors platforms like the MEB+, making it entirely possible to deliver an EV with 450 kilometers of range for a target price of just 25,000 euros. This is exactly the key to finally capturing the urban EV market. Minus 30%, that is a massive number. Because standardizing the box is really only half the battle. How you make what goes inside that box is changing too, leading to a staggering 30% drop in energy consumption during production. For the longest time, making battery electrodes required this wet coating process. You had to use toxic solvents and run everything through massive, 50-meter-long drying ovens. They were huge, energy-hogging thermodynamic bottlenecks. But now, the industry is ditching all that for a dry coating process. It's a direct rolling method that completely eliminates the solvents and those massive ovens. Not only does this cut production energy consumption by that 30%, but it actually shrinks the physical footprint of gigafactories by 15%, which makes them way easier and cheaper to rapidly replicate all over the globe.
Okay, with the manufacturing foundation set, let's move on to Pillar 2, chemistry and packaging breakthroughs. We're going deep inside the cell itself.
You've probably heard the buzz around solid-state batteries, right? But the 2026 benchmark is very specifically the electrodeless solid state, or the anode-free reality. This architecture completely strips away the bulky graphite host matrix you'd find in traditional anodes. Instead, pure lithium metal is deposited directly against a ceramic separator during the battery's very first charge. By getting rid of all that traditional dead weight, you unlock a nonlinear leap in both energy density and weight savings. The real-world validation of this is the QuantumScape QSE5 cell. Look, for a long time there was this myth in battery physics that high energy density and extreme fast charging were just mutually exclusive. You couldn't have both. Well, the QSE5 totally shatters that. It boasts a staggering volumetric energy density of 844 watt-hours per liter while successfully handling a 10C continuous discharge rate and a 12-minute extreme fast charge from 10 to 80%. But get this, even more amazing is the longevity. Because of the incredible mechanical integrity of that solid-state ceramic separator blocking dendrite penetration, validation metrics are showing greater than 95% capacity retention after 1,000 deep cycles. Put that into perspective. In a standard vehicle, that translates to over 500,000 kilometers of driving. This means the battery will practically never age. It'll probably outlast the vehicle itself. Now, solid-state isn't the only game in town for 2026. High-nickel cells, specifically NMC90, are pushing the absolute limits of liquid electrolyte chemistry, hitting an extreme density of 314 watt-hours per kilogram. But this introduces what engineers call the thermal trilemma. If an NMC90 cell enters thermal runaway, peak temperatures can exceed 900 degrees Celsius. In the past, engineers just relied on static physical armor, like heavy aerogels between cells, to stop the heat from spreading. But that passive insulation wastes 5 to 10% of the entire pack volume and adds 1 to 2 euros of cost per cell. It's essentially dead volume and dead weight. So how do we fix this? Ferasis Energy engineered a brilliantly dynamic solution called no TP, or no thermal propagation. Instead of trying to just bottle up 900 degrees with passive armor, they mastered extreme enthalpy routing. They used precise directional venting and integrated cooling to instantly extract that peak thermal energy and safely route it right out of the pack. This dynamic approach completely neutralizes the thermal threat without sacrificing any of that precious dead volume.
Meanwhile, the physical packaging of the pack itself is undergoing its own revolution, leading to what's being called the cylindrical renaissance. Take BMW's Gen 6 system, for example, which utilizes these massive 4695 cylindrical cells. The native compressive strength of these steel cylindrical casings is so incredibly high that the cells transition from just being passive cargo that the car carries around to becoming active, load-bearing components of the car's physical chassis. This pack-to-open body layout opens up 20% more volumetric density and drives a massive 40 to 50% cost reduction in the overall e-drive system.
So the crucial takeaway here is that there is really no single winner yet. Whether we're talking about Volkswagen's unified format, slashing production energy, QuantumScape's solid-state leap in density, Faurecis mastering 900-degree thermal limits, or BMW turning cells into structural chassis elements, they are all just solving different sides of the exact same physics equation. Which brings us to our final pillar, energy integration and topology. Because once you build these ultra-dense batteries, you have to connect them to the grid.
And connecting these batteries requires a massive hardware leap. When you look at the jagged, harsh waveform of a traditional two-level inverter, it's night and day compared to the next-generation modular multi-level converter, or MMC cascade. By dynamically cascading low-voltage modules, it synthesizes a perfectly smooth AC waveform. This near-zero-loss hardware is the ultimate foundation for vehicle-to-grid, or V2G tech. It allows the car to seamlessly act as an active bidirectional node on your local power grid.
But getting energy into these cars rapidly presents an entirely new physics problem. The 2026 roadmap points straight to megawatt charging systems, pushing up to 3.75 megawatts. That requires running at 1250 volts and a mind-bending 3000 amps of current. Pumping 3000 amps creates an extreme joule heating bottleneck. The friction of those electrons is so intense that traditional metal connectors and cooling systems literally just fail and melt at peak loads. No way around it. To overcome that insane thermal limit, engineers are attacking the problem from two sides. First up, dielectric immersion cooling. They are literally immersing the cells and electrical bus bars in a non-conductive dielectric fluid to instantly eliminate thermal resistance. Second, companies are utilizing advanced powder metallurgy. By sintering copper components rather than machining them, they achieve the maximum electrical conductivity required to survive that 3000 amp electrical load without creating a catastrophic bottleneck. All of this brings us to a really powerful conclusion straight from the symposium. They stated, future platform dominance belongs exclusively to OEMs who architect across all three domains simultaneously, eliminating the silos between cell chemistry, thermal packaging, and power electronics. The era of isolated engineering is officially over. Which leaves us with one final, provocative question for you to consider today. With batteries that can charge in 12 minutes, structurally bear the weight of the chassis, never practically age, and seamlessly power your home grid, how will this unified 2026 paradigm reshape the car in your own driveway? The future of energy storage is no longer just about the battery, it's about the entire integrated system. Thanks so much for joining me on this explainer, and keep questioning the physics behind the world around you.
Welcome back to another explainer. Today, we're diving into something absolutely wild. We are decoding the bleeding-edge physical and chemical innovations driving the next generation of electric vehicles. We're pulling all this directly from the incredible insights presented at the 2026 International Vienna Motor Symposium. And honestly, we're going to see exactly how the world's top engineers are completely redefining what is physically possible inside an EV.
Okay, here's our schematic diagram for exploring how the industry is breaking past these physical ceilings. We'll be hitting the 2026 powertrain paradigm, extreme high-speed motor mechanics, the rare earth-free revolution, power semiconductor innovations, advanced packaging and cooling, and finally, ultimate X-in-1 integration. We are literally moving from basic mechanical components to ultimate system mastery.
All right, let's jump right into Section 1, the 2026 powertrain paradigm. Hitting and breaking physical ceilings. We need to establish exactly what the current bottlenecks in EV powertrains actually are.
Look, the industry has basically hit a brick wall with single variable optimization. We just can't tweak one component anymore and expect massive gains. So the 2026 paradigm demands a tightly coupled, system-level approach, specifically a ME-C approach. That means mutually exclusive, collectively exhaustive. To overcome these limits, everything from manufacturing processes to cell chemistry and grid topology has to be optimized together. It's kind of like tuning an entire orchestra instead of just turning up the volume on the guitar, you know?
Moving right along to Section 2, extreme high-speed motor mechanics pushing the rotational limits. Let's see how mechanical engineering is evolving to handle these massive new system demands.
Now, the absolutely crucial point here is this awe-inspiring number, 35,000. Garrett Motion's new 3-in-1 E-axle has pushed motor speeds to an extreme 35,000 RPM. To put that into perspective for you, that is roughly 5 times the red line of a standard sports car engine. Pushing that rotational velocity is literally the most direct physical path to maximizing power density and drastically shrinking the size and weight of the motor.
But, that brings up a really fascinating engineering puzzle. How on earth do you eliminate friction at 35,000 RPM? The mechanical and thermal challenges of spinning a rotor that fast are just immense. I mean, traditional ball bearings would literally melt or tear themselves apart under that kind of extreme physical stress. Well, the solution is oil-free foil bearings. Garrett Motion actually tapped into their decades of aerospace and turbocharger expertise to use these fluid dynamic bearings. Basically, when the rotor spins up, it generates this aerodynamic air film that completely suspends the rotor in midair. There is zero mechanical contact. No way, right? This completely eliminates mechanical friction and prevents high-temperature oil coking.
Okay, Section 3, the rare earth-free revolution, decoupling performance from geography. Let's shift our focus a bit to the magnetic topology of these motors.
So traditional permanent magnet synchronous motors, or PSMs, rely super heavily on rare earth elements, like neodymium and dysprosium. And that means high geopolitical supply chain risk. But look at the alternative here, BMW's Gen 6 EESM. That stands for Electrically Excited Synchronous Motor. It uses absolutely zero rare earth metals, utilizing active electrical excitation instead. What you really need to take away from this is that ESM topology successfully removes those rare earth constraints. But, and this is key, it doesn't sacrifice power. In fact, it delivers dominant highway cruising efficiency through active rotor magnetic field regulation. So we no longer have to choose between supply chain resilience and top-tier driving performance. The engineering has totally bridged the gap.
Right into Section 4, power semiconductor innovations, controlling the current. Stepping out of the mechanical and magnetic domains, we enter the exciting world of power electronics. The broader industry is undergoing a massive shift right now. We're moving away from traditional two-level inverters, which generate high total harmonic distortion, and transitioning to advanced modular multilevel converter, or MMC cascade architectures. This creates the ultimate hardware foundation, setting the stage for very specific microscopic semiconductor breakthroughs. To manage these extreme electrical loads, we look to Bosch's highly technical third-generation silicon carbide MOSFET dual-channel trench architecture. Yeah, that's a mouthful, but think of this microscopic trench as a shield. It protects the delicate gate oxide layer from destructive high electric fields during switching, all while significantly lowering the on-resistance of the transistor.
And the result of that microscopic shield? It directly translates to a massive 20% overall performance boost for the entire inverter system. That's a perfect example of how atomic-level design changes yield huge system-level power efficiency gains for the whole vehicle.
Section 5. Advanced Packaging and Cooling, Mastering Extreme Thermal Loads. Naturally, with extreme rotor speeds and high semiconductor switching frequencies comes extreme heat. To tackle packaging, ZF developed braided winding technology. Traditional hairpin windings waste a ton of axial space at the ends of the stator. Braided winding drastically shortens these ends, enabling ultra-flat motor packaging. It saves about 50 millimeters in width and actually cuts pure copper usage by 10%. Let's look at how ZF layers these innovations in their eDrive systems to master the heat and space constraints. First off, the braided winding reduces axial length. Second, they embed ultra-compact coaxial reduction gears right into the differentials. And third, they apply direct liquid cooling internally, routing it right against the stator copper wire itself. Now, why does this matter to the driver? Well, direct stator cooling pushes continuous power capability to over 75% of the system's peak power. For context,
That means pulling 206 kilowatts continuously out of a 275 kilowatt peak system. It virtually eliminates thermal derating, meaning you get consistent, unrelenting performance on the track or the highway without the system overheating. A real game changer for sure.
Finally, Section 6, Ultimate X-in-1 Integration, the convergence of domains. So, how do all these individual breakthroughs, the foil bearings, the magnetic topologies, the braided winding, and the cooling, how do they ultimately merge?
The absolute imperative here is moving from isolated component engineering to ultimate cross-domain integration. To dominate the future, manufacturers have to architect across manufacturing scale, thermal packaging, and grid topology all simultaneously. Doing things in silos simply doesn't work anymore.
The ultimate realization of this synthesis is the X-in-1 architecture. It eliminates standalone enclosures entirely. It fuses those 35,000 RPM high-speed rotors, the shielded dual-channel SiC inverters, and the tightly braided stators into a single, hyper-dense electric drive axle. The barriers between mechanical, thermal, and electrical domains are just completely erased.
Which leaves us with this final provocative thought. As we hit the absolute physical limits of individual components, whether that's rotational speed, copper density, or semiconductor switching, is ultimate system integration the only true path forward for electric vehicle dominance? The era of simple spec stacking is definitively over. The thrilling future of EV engineering lies entirely in holistic, boundary-breaking design. Thanks so much for joining me on this explainer, and as always, keep learning.
48%. Now, for literally decades, the global automotive engineering community looked at Toyota's 41% brake thermal efficiency and thought, well, that's it. That is the absolute physical ceiling for a mass-produced spark-ignition internal combustion engine. It was basically seen as this unbreakable wall governed by the strict laws of thermodynamics. But, as you're about to see, that wall has just been completely shattered. 48% isn't just some minor incremental update. No, it's a staggering, physics-defining leap that fundamentally rewrites the entire rulebook of power generation. Welcome to today's Explainer. We are diving straight into the bleeding edge of physical engineering, pulling directly from the incredible intelligence synthesized at the 2026 International Vienna Motor Symposium. Today, we're talking about ultimate thermodynamics and high-performance power. The engineers at the symposium, they aren't just tweaking existing systems anymore. They are pushing the physical limits of extreme engineering, trying to squeeze every absolute last drop of energy out of a drop of fuel, and entirely eliminating the mechanical losses that have plagued engines for over a century. Okay, let's dive into this. Here's our roadmap for today. The hybrid powertrain revolution, breaking the thermodynamic ceiling, igniting the 48% BTE engine, Porsche's T hybrid performance leap, and finally, eliminating mechanical parasitic losses. Starting with Section 1, the hybrid powertrain revolution. Moving right into Section 2, breaking the thermodynamic ceiling. So the global transition to electric vehicles isn't really this zero-sum binary choice anymore. The industry has realized that to actually meet strict emissions targets while keeping technical resilience, we're going to need extreme efficiency hybrids. But for the internal combustion engine to even survive inside these new plug-in and range-extended hybrids, it has to achieve unprecedented leaps in efficiency. To break that infamous 41% wall, Chinese automaker Chery partnered up with the Austrian engineering giant AVL, and they literally fundamentally redesigned how an engine moves. Think about the traditional slider crank mechanism. For over a century, pistons have just moved up and down symmetrically, right? The compression stroke and the expansion stroke were mathematically tied together, but Chery and AVL introduced a double-crank, three-link mechanism. By adding this clever offset and a complex linkage, they entirely detached compression from expansion. It creates an asymmetric stroke. This means the piston actually drops incredibly deep during the power stroke to squeeze out every last drop of energy, and they managed to do this all without increasing the actual height of the engine block. And honestly, this is just a brilliant illustration of the ultimate evolution of the Miller cycle. Traditionally, the Miller cycle simulates a longer expansion stroke by kind of messing with the valve timing. But with this new mechanical linkage, that thermodynamic concept is taken to an absolute physical extreme. You aren't just faking a longer expansion stroke with valves anymore. The actual physical geometry of the piston's travel is physically forcing those expanding gases to do vastly more mechanical work before they ever escape out the exhaust. Now, when you combine these mechanics, the resulting numbers are just staggering. The expansion ratio leaps from your standard 14-to-1 all the way to an unbelievable 26-to-1. And to fuel that massive chamber, they had to crank the fuel injection pressure from 350 bar up to a bone-crushing 600 bar, just to instantly atomize the fuel. Plus, check out the exhaust gas recirculation, or the EGR rate. They pushed that from 20% up to a massive 35%. Guys, these aren't just iterative improvements. These are monumental jumps in engineering that make that 48% efficiency physically possible. All right, Section 3, igniting the 48% BTE engine. So having a 26-to-1 expansion ratio and flooding the cylinder with 35% inert exhaust gas, well, that creates a complete nightmare scenario for ignition. The mixture becomes so diluted that a traditional spark will literally just fizzle out. And if you can't ignite that mixture rapidly and uniformly, you're going to get catastrophic engine knock and complete power failure. To solve this, the engineers turned to Bosch's passive pre-chamber ignition. It's wild how this works. The whole process actually starts outside the main action. As the piston rises, it forces a tiny bit of the fuel-air mixture into a micro pre-chamber that's wrapped directly around the spark plug. The spark fires in that tiny enclosed space, which causes an immense, instantaneous pressure spike. And then here's where the magic happens. That pressure violently forces the combusting gases through these tiny nozzles, shooting supersonic reactive plasma jets deep into the main cylinder. It cures engine knock completely because it creates instantaneous, volumetric ignition across the entire chamber. It is literally like setting off a dozen tiny grenades rather than trying to light a single match in a windstorm. Section 4. Porsche's T-Hybrid Performance Leap. Let's shift gears for a second. Moving from the ultimate quest for commuter efficiency to the absolute pinnacle of track performance, Porsche unveiled their 992.2 generation 911 Turbo S. This beast features a brand new 3.6-liter flat-six engine paired with a T-hybrid system that churns out a massive 701 horsepower. And that brings us to a really strategic number, 400 volts. Now, the rest of the industry is kind of blindly chasing 800-volt systems for absolutely everything right now, but Porsche purposely chose a 400-volt system for this track monster. Why? Because the T-Hybrid relies on a tiny, ultra-lightweight 1.9 kilowatt-hour battery. If they used an 800-volt architecture for a battery that small, they would have had to stack so many cells in series that the internal resistance and packaging weight would have completely ruined the car's dynamic handling. So 400 volts perfectly matches this battery, keeping the car incredibly light and aggressively fast. To really understand where a good chunk of that 701 horsepower comes from, we need to talk about exhaust enthalpy. Basically, that's the total heat and kinetic energy contained within the high-pressure exhaust gases leaving an engine cylinder. Now, usually a huge portion of this enthalpy is just dumped right out of the tailpipe as wasted heat, but Porsche actually took a page straight out of the Formula One playbook to capture it. They created what's called the bypass valve-free E-turbo, and the engineering sequence here is honestly mind-bending. When you stop on the gas, an electric motor that's built directly into the turbocharger shaft instantly spools the compressor. That literally eliminates turbo lag. Then, as the exhaust gases start building up, they take over spinning the turbine. But the real stroke of genius happens right after that. Once the exhaust is flowing at peak velocity, that same exact electric motor instantly converts into a generator. It harvests the excess exhaust enthalpy and feeds it right back into that 400-volt battery. By removing the traditional mechanical wastegate entirely, Porsche subjected the turbine to some terrifying thermal stress, for sure. But by doing so, they unlocked a totally closed-loop energy system. Section 5. Eliminating mechanical parasitic losses. So look, whether you're generating ultra-efficient power like Chery or track-destroying power like Porsche, it is completely pointless if that power is just lost to friction before it even hits the wheels. Tying these incredibly complex systems of electric motors and combustion engines together requires revolutionary drivetrain hardware. Enter the Amstead Automotive Dynamic Controllable Clutch, or the DCC. See, when a hybrid is driving in pure EV mode or just coasting, the traditional engine and gears are still physically connected. They're churning through thick oil and creating massive parasitic drag. The DCC solves this by firing a micro-electromechanical actuator that completely decouples the transmission paths in milliseconds. I'm talking dropping parasitic losses to absolute zero. It is a pure, frictionless disconnect, enabling the entire system to seamlessly weave between electric and combustion power without wasting a single watt. Stepping back to look at the big picture for a moment, a core theme of the symposium was captured in this idea. The era of single variable optimization has hit physical ceilings. The 2026 paradigm demands a tightly coupled system-level approach. We really can no longer just tweak a spark plug or make a battery slightly bigger. To achieve 48% thermal efficiency or 701 horsepower hybrids, these engineers are having to optimize the thermodynamics, the chemistry, the high-voltage electronics, and the mechanical materials all at the exact same time. It's a holistic masterpiece. Which leaves us with this final, massive question to ponder. Has the internal combustion engine actually reached its absolute physical limit with these 2026 breakthroughs? Or is this hyper-efficient, high-performance hybrid era literally just getting started? I mean, think about those supersonic plasma jets and zero-loss mechanical clutches. The boundaries of physics are being pushed further than we ever thought possible. Thank you so much for joining me on this explainer today, and keep your eyes on the road ahead, because the engineering is only going to get crazier from here.
Okay, let's jump right into this explainer and deconstruct some truly groundbreaking stuff coming out of the 2026 Vienna Motor Symposium on the future of heavy-duty transport. Now, for years, the narrative we've all heard has been pretty straightforward, right? The future is electric, period. But when you get over 1,000 of the world's top powertrain engineers and R&D architects in one room, that simple consensus totally shifts into complex thermodynamic realities. Today, we are looking at the literal engineering resurrection of advanced combustion and alternative fuels. Let's get into it.
So, we've got to start by challenging a really major assumption today. Is pure battery electric truly the sole solution for zero-emission commercial vehicles? I mean, if you're looking at passenger cars, yeah, batteries have pretty much won the argument. But when we talk about the hard-to-abate sectors, think massive, heavy-duty trucking, non-road mobile machinery, huge maritime transport vessels, batteries actually hit a really harsh physical ceiling. The extreme weight of those massive battery packs just severely punishes payload capacity, and honestly, the charging infrastructure demands are monumental. The industry has finally realized we need a resilient, multi-energy technology portfolio if we want to truly decarbonize.
Take a look at this number, 60%. What's really wild about this is that 60% is the jaw-dropping theoretical brake thermal efficiency target for the new wave of hydrogen internal combustion engines. To put that into perspective for a second, traditional diesel engines have been hovering right around the 50% mark for years, literally fighting tooth and nail for every tiny fraction of a percent. So hitting 60% efficiency, that wouldn't just be some incremental update, it represents a historic leap in thermodynamics, putting hydrogen combustion absolutely neck and neck with fuel cells, but with some massive industrial advantages.
All right, here's our roadmap for today. We're covering 1. The zero-emission heavy-duty shift. 2. Commercializing hydrogen combustion. 3. High-pressure direct injection. 4. Nanoscale coatings. And 5. Cryopumping and ammonia.
Starting with Section 1, the zero-emission heavy-duty shift. Let's see how they're keeping IC alive.
The absolutely crucial point here is that manufacturers can utilize their existing multi-million-dollar diesel infrastructure to build hydrogen engines. It makes the transition incredibly practical. Think about the global supply chain for a minute. The casting facilities, the tooling, the complex assembly lines. Shifting that entire global industry exclusively to fuel cells or massive battery packs overnight, that requires unimaginable capital expenditure. Hydrogen internal combustion, or H2IC, basically allows the industry to bypass stranded assets altogether. It's this brilliant commercial mass production strategy that delivers zero-carbon heavy-duty transport rapidly and economically.
Moving to Section 2, high-pressure direct injection breakthroughs. This is the system-level innovation making it all possible.
Walk through this process with me. The HPDI system starts by injecting a tiny amount of diesel as a liquid spark plug right before blasting in the hydrogen. Here's why. Hydrogen has an incredibly high auto-ignition temperature, so it's super hard to ignite purely by compression alone. So, right at the very end of the compression stroke, a proprietary dual concentric injector sprays a microscopic amount of diesel, we're talking just 1 to 3% of the total energy. This auto-ignites under the intense pressure, creating a robust liquid spark plug. Immediately after, bam, hydrogen is blasted directly into that flame at an immense pressure of around 300 bar.
Now contrast HPDI's late-cycle diffusion flame with the old traditional premixed flames used in port fuel ejection. In the old method, hydrogen was mixed with air in the intake manifold, which had fatal flaws like backfire and pre-ignition. Because hydrogen ignites so ridiculously easily with just a tiny spark or hotspot, those older methods often saw the gas literally explode before the valves even closed. Obviously, that's incredibly destructive. With HPDI, the engine only compresses pure air. The hydrogen is introduced so late in the cycle that pre-ignition is physically impossible. This neat trick allows engineers to run incredibly high compression ratios, drastically amplifying the engine's power density.
And the testing results? They are staggering. Real-world data from heavy hitters like AVL, Scania, and Westport shows that HPDI hydrogen engines have already hit 52.5% efficiency. That surpasses base diesel platforms. They aren't just matching diesel anymore, they are actively beating it. And because hydrogen's molecular diffusion rate is so incredibly high, it mixes and burns with explosive speed once injected. It releases its heat exactly when the piston needs it most. This delivers the massive low-end torque that is absolutely essential for heavy trucks, all while emitting zero CO2.
All right, Section 3, Nanoscale Coatings. We've got to talk about stopping hydrogen embrittlement.
This is a terrifying physical phenomenon. Because hydrogen molecules are so unimaginably tiny, they literally infiltrate high-strength steel and tear the engine apart from the inside out. When exposed to the extreme pressures and temperatures of HPDI, hydrogen molecules actually dissociate into individual atoms. These atoms slip right between the iron atoms and the steel lattice of the fuel injectors and piston rings. They gather at microscopic defects, recombine back into gas, and build up this immense internal pressure until the metal just snaps. No warning at all. Add in the fact that hydrogen is a perfectly dry gas with literally zero lubricating properties, and your high-pressure fuel system is basically a recipe for instant mechanical failure.
But engineers are fighting back at the molecular level. The solution lies in advanced surface engineering. Diamond-like carbon, or DLC, coatings seal the metal and provide crucial solid self-lubrication. Using physical and chemical vapor deposition, companies like Ion Bond are applying nanoscale films directly to these engine components. These coatings are entirely pinhole-free, acting as an impenetrable microscopic fortress that blocks those tiny hydrogen atoms from ever entering the steel. And it gets better. The diamond-like carbon provides its own dry lubrication. Even without a single drop of oil, the friction coefficient drops below 0.05. That allows those extreme high-pressure injectors to fire millions of times without wearing out.
Which brings us to Section 4, cryopumping and ammonia storage. Let's zoom out to the macro infrastructure level.
Handling liquid hydrogen requires incredible infrastructural innovations because it has to be kept near absolute zero. Think about it. Moving liquid hydrogen at 20 Kelvin, that's negative 253 degrees Celsius. It requires pumps that won't just instantly shatter from the thermal shock or leak. Bosch Rexroth's cryopump breakthrough is huge here. It drastically reduces the parasitic energy loss that's usually associated with compressing and pumping hydrogen, and it's actually hitting the 20,000-hour durability metrics required for real-world commercial fleet operators.
But check out this comparison. When you compare liquid hydrogen directly against ammonia, you see exactly why ammonia is such an incredibly attractive, easy-to-store chemical carrier for heavy transport. Look at the numbers. Liquid hydrogen requires deep, energy-intensive cryogenics. But ammonia? It's basically a hydrogen carrier that behaves beautifully. It liquefies at just negative 33 degrees Celsius or a super mild 8.6 bar of pressure at normal room temperature. Plus, we already have a massive global infrastructure for shipping ammonia for fertilizers. So for maritime shipping and long-haul transport, ammonia offers a volumetric energy density that makes tremendous economic sense.
There is a catch, though. While ammonia is super easy to store, it is notoriously difficult to burn. That's why engineers are turning to dual-fuel pilot injections to force stable combustion. Ammonia has a painfully slow flame speed and is extremely reluctant to ignite. But engineers are applying similar pilot ignition strategies here, using that tiny spray of diesel to kickstart the reaction. Combine that with highly complex in-cylinder charge motion and ultra-precise post-injection timing, and you ensure the ammonia burns completely, without leaving toxic slips or generating excessive nitrogen oxides. It is an absolute masterful manipulation of combustion kinetics.
Ultimately, the future isn't about finding a single winner. It's a unified paradigm where batteries and advanced combustion coexist side by side. What we are really seeing from the 2026 Vienna Motor Symposium is the death of the one-size-fits-all engineering mindset. The strategic imperative moving forward requires fully integrating manufacturing scale, thermal packaging, and multi-energy fuel platforms. It's all about matching the exact right thermodynamic tool to the right mobility task. So, I want to leave you with this final, provocative thought to ponder. As these paradigm-shifting innovations begin to directly impact the vehicles we rely on every single day, as internal combustion is literally reborn at the nanoscale, which multi-energy technology will power your fleet tomorrow? Will it be unified battery cells for urban transit, high-pressure hydrogen injected into massive heavy haulers, or ammonia-powered maritime vessels? The engineering resurrection is here, and the future of power is vastly more dynamic than we ever imagined. Thanks for joining me on this explainer.
and keep questioning the limits of what's possible.
Welcome to this explainer. Today we're unpacking a truly profound paradigm shift that is happening right now in the automotive industry. We are officially moving away from the century-old concept of cars as purely mechanical objects, or, honestly, even just machines with a few computers jammed into them. Instead, as revealed at the 47th International Vienna Motor Symposium, the vehicle of 2026 is fundamentally transforming. It's becoming a continuously evolving, probabilistic AI platform on wheels. So, if you want to understand exactly where mobility, advanced engineering, and top-tier cybersecurity are about to collide, let's get started. Okay, let's dive into this. Here is our agenda for today, to help us break down this massive transition. 1. The SDV blueprint. 2. Zonal architecture. 3. AI safety in NIS2. 4. PGNN and agentic AI. And finally, 5. Digital twins. Starting off with Section 1. The SDV blueprint. We're mapping the 2026 automotive paradigm shift. And this brilliantly illustrates exactly what we're talking about. The 2026 vehicle is no longer hardware bound. It is literally a software-defined supercomputer. Notice those high-bandwidth Ethernet backbones running the entire length of the chassis? They connect everything directly to a central compute core and a dedicated AI engine. You have to realize, this isn't just some minor wiring upgrade. It's a complete reimagining of the car as a centralized data center, one that's capable of seamless over-the-air updates and, crucially, fail operational safety. Now, to make sense of all this incredible complexity, we're going to split this revolution into two distinct pillars. Pillar 1 is onboard execution. So that's everything happening inside the physical car out there on the highway. Pillar 2 is offboard engineering, which is the massive creation process happening back in the AI-driven labs and cloud simulations where these vehicles are actually born. Moving to Section 2, zonal architecture. Time to declutter the onboard compute. For decades, legacy vehicle architecture was, well, basically a spaghetti network. You had over 100 isolated electronic control units, or ECUs, scattered all over the car, constantly fighting over static, incredibly slow routing protocols. It was an absolute nightmare for trying to run complex AI. But compare that to the sleek, decoupled 4SDV zonal architecture. Instead of 100 tiny, confused brains, you now have one central high-performance computer delegating tasks to localized zonal control units. These edge units can actually filter raw data locally using built-in neural processing units, totally decluttering the network. It's a real game changer. Now, what's really interesting about this slide is how these decoupled systems actually talk to each other. They communicate through what's known as a golden triangle of network protocols. You've got DDS acting as the traffic cop for publish-subscribe quality, TSN guaranteeing microsecond deterministic latency, and Xenos seamlessly binding it all to the cloud. So when a sensor detects an obstacle, this golden triangle ensures that the data is processed right there at the edge, in mere microseconds, without ever clogging up that central computer. All right, Section 3, AI safety and NIS2, governing the probabilistic machine. Let's address the elephant in the room. AI in life-critical systems suffers from something we call functional insufficiencies. You see, unlike traditional software, AI doesn't really have bugs in the classical sense. Its flaws actually come from the data it was trained on. Old deterministic safety rules assume code is either perfectly right or perfectly wrong. But AI, it operates on probability. If an AI encounters a totally bizarre new scenario on the road, an out-of-distribution event, your legacy code validation simply cannot protect you. To fix this massive vulnerability, the industry is quickly adopting the new ISO Pass 8800 standard. This standard kicks off with a continuous data-centric V-model, basically treating massive datasets with the same ruthless, demanding rigor as hardware testing. But because we can't mathematically prove that an AI is 100% flawless, we rely on a safety cage architecture. If the AI's output starts acting unpredictably or its confidence level drops, this rigid deterministic cage instantly intercepts the command, overrides the AI, and triggers a graceful degradation to a safe state, like initiating emergency braking. And the governance doesn't stop at physical safety. It extends right into aggressive network security. The EU NIS2 directive is forcing a brutal wake-up call for the entire automotive sector. We are literally talking about board-level legal accountability, where executives can be held personally liable. Fines can reach up to 10 million euros or 2% of global turnover. And if there's a breach, You don't get weeks to investigate. You have exactly 24 hours to file an early warning and 72 hours for a detailed scope report. So, the crucial point is that this regulation doesn't just apply to the massive automakers. The mandate forces a zero-trust supply chain cascade all the way down to Tier 3 suppliers. By using SPIF and SPIFE, microsegmentation, lateral movement across the vehicle's network is completely blocked unless a component has a valid cryptographic identity. Meaning, even if a tiny third-party sensor manufacturer gets hacked, the zero-trust cascade prevents that vulnerability from ever reaching the main vehicle. Let's move to and see how this builds into Section 4, PGNN and Agentic AI, the offboard creation process. Shifting gears over to our second pillar, offboard engineering, we face a massive hurdle. How do we get these giant AI models to actually run inside a car's limited hardware? The absolute best solution is PGNNs, or physically guided neural networks. Think of this as the ultimate compression technique. It takes these gigantic, highly complex AI models trained in the cloud and shrinks them down into incredibly efficient, interpretable lookup structures that can instantly run on physically limited chips at the edge. So how does it work? Through dimensional reduction algorithms, that massive cloud-trained PGNN is essentially reverse-calibrated into a lean, explicit lookup table, or LUT, and the result? A stunning 17% increase in predictive accuracy for real-time controls, like preemptively managing battery thermals, all without melting the onboard electronics. It is quite literally giving the car a supercomputer's intuition on a microchips diet. Meanwhile, the engineers designing these systems are undergoing their own massive revolution through the Agentic AI maturity model. R&D is shifting rapidly from manual human CAD work to completely autonomous workflows. It starts at level 1 with simple AI copilots helping generate code, but it scales aggressively through task agents to multi-agent workflows up to a cognitive layer that balances multi-physics conflicts, all the way to level 5 pathfinding. At level 5, the AI autonomously derives the entire system architecture based on performance boundaries. Engineering itself is literally being re-engineered. Finally, Section 5, Digital Twins, unifying virtual agility with physical reality. Virtual simulations are incredible, for sure, but they simply aren't enough for the brutal physics of 2026's high-voltage systems. Enter the copper car rig. This is the vital bridge between the cloud and the road. It performs physical-level regression testing using actual high-voltage cables and dummy loads. Before an over-the-air update is beamed to millions of customer vehicles, it has to run through this physical copper car to guarantee that agile cloud software doesn't trigger a catastrophic real-world hardware failure. Bringing this all together, there are 3 strategic imperatives for any engineering C-suite watching right now. 1. You must mandate high-fidelity digital twin integration from all your suppliers. 2. Restructure your R&D departments right now to leverage agentic AI workflows to break the human compute bottleneck. And 3. Acknowledge the probabilistic nature of AI and immediately implement ISO PS 8800 safety cages on all your critical systems prior to deployment. We are stepping into an incredible era where the software defines the vehicle, but the data defines the safety. As we leave you today, take a hard look at your own ecosystem. In a zero-trust, software-defined world, is your supply chain truly ready to deliver a perfect digital twin? Thank you so much for joining me on this explainer. Keep asking the hard questions, and I'll see you next time. Welcome to this explainer. Today, we're diving straight into what is honestly an absolute earthquake in automotive engineering. We'll be synthesizing some of the most critical insights straight from the 2026 International Vienna Motor Symposium. You know, for decades, vehicle compliance was basically just a mechanical problem, right? It was a physical, tailpipe hardware fix. But as we're going to see today, the upcoming Euro 7 regulations are forcing a complete, ground-up transition to a cradle-to-grave, deeply integrated digital ecosystem. Okay, let's dive into the core thesis behind this massive industry shift. Those single technology bets, like relying purely on battery electric vehicles, those are officially dead. What global OEMs absolutely require now is a highly resilient technology portfolio, and it's driven by a very specific 4-pillar architecture. We're talking continuous lifecycle monitoring, tackling non-exhaust emissions, cryptographic digital compliance, and dynamic lifecycle carbon assessment. Literally, we need all 4 of these functioning together just to survive the Euro 7 era. To really get a handle on all of this, we're going to take a bit of a journey. First, we'll look at the Euro 7 paradigm overall. Then we'll zoom all the way inside the vehicle's digital brain for continuous lifecycle monitoring. After that, we zoom out to the physical wheels to solve non-exhaust emissions. Check out the digital vehicle passport, zoom way out beyond the tailpipe, and finally, map out the road to 2030. Starting with Section 1, the Euro 7 paradigm. We are officially moving from hardware exhaust to a digital ecosystem. To really wrap our heads around the sheer scale of this engineering shift, we just need to look at the stark contrast between the old rules and the new ones. In the legacy Euro 6 era, regulators basically tested a physical car on a dyno for 100,000 kilometers, slapped a physical tamper seal on the parts, and called it a day. Well, Euro 7 totally throws that out the window. It now demands 200,000 kilometers of real-world dynamic telemetry. That spans 10 full years, and it all has to be secured by SHA-256 cryptographic hashing. It's no longer just about chemistry anymore, folks. It is entirely about data. And that brings us perfectly into Section 2. Continuous lifecycle monitoring with OBM and Edge AI. Let's zoom right into the vehicle's onboard computer to see how this 24/7 surveillance actually works in practice. And this brilliantly illustrates the massive physical bottleneck that legacy hardware faces. Physical exhaust sensors simply degrade over 200,000 kilometers. Plus, they constantly run into cross-sensitivity issues. So what's the solution? It's software-defined Edge AI. By utilizing advanced algorithms, like extended Kalman filters and mixture of experts, the vehicle's onboard neural network mathematically extracts pure emission signals, things like NOx and ammonia, in under 1.5 milliseconds. We are quite literally replacing physical metal with pure math. But here's the catch. This AI isn't just passively watching. It has some incredibly heavy legal teeth. The onboard monitoring, or OBM system, is active 24/7. Now, if your vehicle detects that its emissions exceed 2.5 times the legal limit, it doesn't just quietly turn on a check engine light on your dash. No way. The system legally mandates an automatic performance reduction. And the ultimate penalty? The vehicle will physically prevent engine ignition. It will literally stop the car from starting until it's fixed. Just imagine waking up and your car refusing to start for work simply because it failed its own internal math homework. Let's move to Section 3 and zoom back out from the car's computer to its physical feet. It's time to talk about solving non-exhaust emissions. And this naturally brings up a pretty fascinating question, one that's often called the EV paradox. Think about it. If an electric vehicle doesn't even have a tailpipe, why is the Euro 7 framework heavily regulating it as a polluter? Well, the answer is right there on the wheels. You see, the increased mass from those heavy battery packs, combined with that instantaneous torque we all love, heavily amplifies non-exhaust emissions. We're specifically talking about micro-abrasive brake dust and tire road wear particles. These are actually eclipsing tailpipe outputs now. Think about that the next time you hit the brakes hard at a stoplight. That physical friction has a highly measurable environmental cost. In fact, Euro 7 sets an absolutely unprecedented new limit. Battery electric vehicles are now restricted to generating just 3 milligrams per kilometer of brake dust. So, how exactly do engineers solve this paradox? It requires some pretty radical mechatronic solutions. For instance, manufacturers can use extreme high-speed laser cladding on brake rotors. Now, that cuts dust by roughly 90%, but it comes at a really high cost. For the mass market, thermal diffusion techniques like Smart ONC are much cheaper and offer moderate reduction. Or, if they want to go all out, they can completely disrupt the wheel architecture with active enclosures. Take the ZDO-1 project, for example. It actually vacuums and filters out near 100% of brake dust right at the wheel. It's a total game changer. Okay, now that we've covered the physical emissions, let's look at Section 4, the digital vehicle passport, and how all this complex data is actually governed. So, the crucial point here is the Environmental Vehicle Passport, or EVP. Let's be clear, this is not just a printed piece of paper you shove in the glove box. It is a mandatory, completely immutable, cryptographically secured digital twin. It's basically a digital ghost that lives right alongside the physical car for its entire life. The data payload inside this passport tracks the static factory baseline, sure, but much more importantly, it dynamically monitors lifetime fuel consumption and legally mandated battery health. And here is the real kicker. This information must be universally accessible. Consumers and regulators aren't going to need expensive proprietary diagnostic tools anymore. They can access this highly secure UN R155 compliant data matrix via a simple, unhackable QR code right on the dashboard. Next up, we're zooming all the way out to the macro level for Section 5, beyond the tailpipe, diving into dynamic life cycle assessment. Now, what's really interesting about dynamic life cycle assessment is this exact number, 68,000 kilometers. Because manufacturing a massive 4-ton battery pack requires such an immense amount of energy up front, an electric heavy truck essentially starts its life in a massive carbon debt. Based on the current European energy grid mix, that electric truck has to drive 68,000 kilometers, which is roughly 6 months of continuous long-haul driving just to break even on carbon parity with a modern, highly efficient diesel truck. And that is exactly why static yearly emission averages are totally dead. The new paradigm, this dynamic LCA infinity loop, demands high-resolution hourly tracking. We now have to calculate emissions based on real-time hourly grid energy mixes, how local weather impacts battery efficiency, and the actual real-world movement trajectories of the fleet, spanning all the way from initial mining to final recycling. Which brings up a pretty vital truth. Merely replacing new cars just isn't enough to hit our global climate goals. We still have a massive existing combustion engine fleet already out there driving on the road today. So, to fully close the carbon cycle, the industry is heavily looking into extreme thermodynamics and drop-in e-fuels. This creates a closed-loop system where carbon that's captured directly from the air is synthesized into zero-emission fuel, which can then be dropped right into existing vehicles. Finally, let's bring all these dense concepts together in Section 6, the road to 2030, mapping out exactly how the industry plans to execute this transformation. Let's walk through these compliance milestones to see how it all builds over time. In the immediate term, meaning 2026 to 2027, OEMs absolutely must deploy those AI virtual sensors we talked about and lock down their over-the-air or OTA cryptographic pipelines. Then, by 2028, the engineering focus shifts down to the physical chassis, integrating active control systems just to meet those strict new tire wear limits. And looking out to 2030 and beyond, we'll see a complete transition to zonal software-defined vehicle architectures, which finally enables total fleet-wide AI optimization. Which leaves us with this final, incredibly provocative thought. We've seen exactly how Euro 7 is forcing this monumental shift from physical exhaust mechanics to full life-cycle, cryptographically secured digital governance. The math is pure, and the AI is incredibly fast. But the ultimate question is the massive, deeply entrenched physical global supply chain actually ready to move at the speed of software? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.